Continuity, Part 6. We need to somehow show that the number the square root of 2 exists. And we're going to do this using the intermediate value theorem. But this is kind of tricky to figure out where does this square root of 2 fall in the intermediate value theorem. So the conclusion of the intermediate value theorem is there exists a number c in AB such that f of c is equal to n. So if we have proving the existence of c such that f of c is equal to n, that means we're trying to show that we have f of the square root of 2 is equal to n. So we need to figure out some sort of function and some sort of n, and then these a's and b's so that we can show this square root of 2 exists. So again, we need to find a continuous function, an output between f of a and f of b for that interval where our function is continuous, and f of a cannot equal f of b. If we can show those things, then we can conclude that there exists a number c in AB such that f of c is equal to n. When you're trying to show that a number exists, you need to temporarily suspend your belief that the number exists. So we're going to go, I am not quite so sure that the square root of 2 is actually a number. I'm not sure that you can take the square root of 2. I know you can take the square root of perfect squares, but 2 isn't a perfect square, so I'm just not quite sure this is a real number. I think you made it up. But if it did exist, then it would be the solution or some sort of input to a function for a particular output of that function. And we have to go, well, what function do we know of that would be really easy to undo a square root? We believe in square roots, just not necessarily the square root of 2. Well, the inverse of square rooting is squaring. So if we had f of x is equal to x squared, that would mean that f of the square root of 2 is equal to the square root of 2 squared, which would be equal to 2. So if the square root of 2 is actually a number, and it exists, then it's going to be the solution to the equation x squared is equal to 2. So we have our function, and we have our output, and now we just have to find an interval so that we can use the intermediate value theorem. But we have the main things that we need, so we can move on to stating the intermediate value theorem. Okay, so to show the number the square root of 2 exists, we need to show that x squared equals 2 has a solution. And we'll do this using the intermediate value theorem. So let's start by stating the intermediate value theorem. So suppose f is continuous on the closed interval from a to b, and let n be any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c in the open interval a to b such that f of c is equal to n. Now to state and justify continuity. So let f of x equal x squared, which is continuous over the interval from negative infinity to infinity, because it is a polynomial. You could also say it's a quadratic function, but polynomial works. And now we need to find like the smaller interval that we're actually interested in here to narrow in on where this square root of 2, if it really exists, would be. So we need to find, in this case, an a and b, as well as an f of a and an f of b. And we need these f of a's and f of b's to be on either side of our n, which is this 2. So we need outputs for x squared that are smaller than 2 and larger than 2. So if we just look at half of our x squared, and maybe you'd prefer if I drew some points here. So 1, 2, 3, 4. 1, 2, 3, 4, 5. So we have the point 0, 0, 1, 1, 2, 4, and then I don't even have room for 9 over there. So here's f of x is equal to x squared. And then we also have the other side of our parabola. And we're trying to show the number squared of 2 exists. So we have this n at 2. And we're trying to show that the square root of 2 is actually a number. So we need to find f of a and f of b on either side of this. Well, 1, which is 1 squared, is smaller than n, and 4, which is 2 squared, is slightly larger than our n of 2. So we can use f of 1 is equal to 1, and f of 2 is equal to 4. And we have our f of a and f of b that are on either side of this 2. Now all that's left is to state our conclusion. And like with any good paper, we want to, in our conclusion, have like a little summary of what we just did here. So, since f of x is equal to x squared is continuous on the closed interval from 1 to 2, and those were our inputs that we found. That's our a and b. And f of 1 does not equal f of 2. And 2 is between f of 1 and f of 2. There must be some number c on the open interval from 1 to 2 such that f of c is equal to c squared is equal to 2. Thus, c is equal to the square root of 2 exists by the intermediate value theorem. And notice that we don't have an exact number for the square root of 2. We know it's somewhere between 1 and 2, but this doesn't tell us exactly what the square root of 2 is. And we can come up with decimal approximations for the square root of 2. But this symbolic representation here is actually as exact as the square root of 2 is going to get. And when you get a number out of your calculator that has a bunch of decimal places, that's an approximation of the square root of 2. It's a pretty good approximation, but it's not exact.